simple harmonic motion with two springs. So the obvious question is, well, if I attach two springs to a mass spring system, what is the effective spring constant on the system? So we actually have three cases, three possibilities. Case one, as I call it, we have two springs on one side of the mass. So if we take this mass and pull it to the right a distance of x, these two springs stretch at the same time. Now, the two springs could be different or they could be the same. As m is moved to the right a distance x, two restoring forces act on the system, F1 and F2. So now two forces, kind of like in this tug of war. I pull in this direction and the two springs want to restore the position of mass m. So these two forces added together, they are equal to negative k1x plus negative k2x. We're using the same x is because both are kind of fighting this, this pull that I'm producing on mass m. So effectively, what we can do is we can factor out the k value, and the effective force, that means the sum of those two forces, is going to be equal to the sum of the spring constants. So the effective spring constant is just the sum of those two. So a single spring with an effective spring constant can have the same effect as two springs with two separate spring constants. So we can actually replace that with a single spring. So case two, what if we took springs and would put it on either side of the mass? So two springs on either side. Again, these springs could be the same spring with the same spring constant, or they can be different. So if we take this mass and pull it to the right a distance of x, that means that this spring is stretched a distance of x, and this spring on the right is compressed a distance of x. So it doesn't really matter. Either way, we have a restoring force on this side, and we have a restoring force on that side. So two restoring forces act together to return the mass back to its original start point. F1 pulls the mass to the left, and F2 pushes the mass back to the left to restore its position. So again, we're just going to be adding those two forces, and just like we did with case one, in the end, the effective spring constant is just the addition of those two individual spring constants. Exactly the same as case one. Now case three, what if we were to take two springs and connect them in series? When we make a chain of things, we call that a series. So we have, if I take this mass here and I pull it to the right a distance of x, what happens is I'm using color coding here, the green spring, spring 1, stretches a particular distance x, and spring 2 stretches its own distance of x. If the two springs were identical, the x's would be the same. However, if they are different, and that's kind of the point of this lesson, let's assume that they are different, these two will stretch different lengths. So note that if the stretch distances are different, then the spring constances will be different. So they stretch different amounts. So this x right here is equal to these two distances added together. So x is equal to x1 plus x2, the total stretch. This stretches a bit and that stretches a bit. Those two stretches add up to the full movement that you pull the mass over to the right. So I'm just going to go over to this box right here. I want to emphasize something. Since this is one continuous series of springs, it's kind of like two ropes attached to one another. The tension in that series is going to be uniform throughout. What will happen is the two springs, depending on the spring constant, will compensate for the force acting on them. And regardless, it'll be the same force. So it's the same tension in both series. So this would be spring 1. Its tension is going to be negative K1 X1, or X1 is going to be the ratio of the force divided by the spring constant. And the second spring will also have the same force in it, the same tension. That's going to be equal to negative K2 x2. So x2 is equal to the ratio of F over K1. The reason I'm writing this here is because I want to plug that into this formula. Because we said that the distance this is stretched is equal to these two distances. So I wrote those two distances in terms of the tension and their respective spring constant values. So we're just going to plug and chug here and expand this and simplify this. And then we see that the effective spring constant is equal to the product of the spring constant divided by the sum.